We are the paradoxical ape. Bipedal, naked, large-brained, long the master of fire, tools, and language, but still trying to understand ourselves. Aware that death is inevitable, yet filled with optimism. We grow up slowly. We hand down knowledge. We empathize and deceive. We shape the future from our shared understanding of the past. CARTA brings together experts from diverse disciplines to exchange insights on who we are and how we got here. An exploration made possible by the generosity of humans like you.
Let me begin my talk on learning by experimenting. Let me start with a question. What requires more intelligence? Playing a game of chess, or perhaps opening a door? Now, humans might think that playing a game of chess requires more intelligence. Let's look at what we know from artificial intelligence. We have heard about AI systems which have beaten the best humans at the game of chess. They have become better than humans at playing multiplayer games, and more recently, beating humans at the very tough game of Go. Right? And there's been a lot of buzz about ChatGPT, which is super impressive. For example, you can ask a question, the Coke is in, and it's going to complete an answer. For example, in the fridge with rest of the food. Very reasonable. You can also ask it many more complicated questions. For example, write an outline for a talk on continual learning robots for anthropologists. And it will give you something reasonable. Now, while we are in the virtual world, the world of games, the world of language, we have achieved impressive results. But for a moment, let's go and see our progress in the physical world. Now, when we put our latest and greatest robots to do some of the tasks we do every day, like opening doors, climbing on stairs, this is what happens. This is not the worst videos or the worst robots I am showing you. These are, in fact, the videos from winning teams in a challenge that DARPA organized maybe 7 to 8 years ago. Not much has changed since then. These robots can't perform the daily tasks that humans can perform even without thinking. Now, why is this? Now, many people have thought about this question. It's very well put in by Hans Moravec. He says that reasoning requires very little computation, but sensory motor skills require enormous compute. Put in other words by Steven Pinker, he says the main lesson of 35 years of AI research is that hard problems are easy and the easy problems are hard. Things like chess, which we think to be hard, are actually quite easy for computers. But things like opening a door or climbing stairs, which we think are very easy, have proven very hard for AI machines. And this observation has been known as the Moravec's paradox. The Moravec's paradox was first noted in around 1988, right, around 35 years ago. And today, 35 years have passed, and let's see what progress we have made. So what I'm showing you is a video put out by Google in an impressive work where they're getting this robot to do some household tasks. So if you look at the text on the bottom left, it says, I spilled my Coke on the table. How would you throw it away and bring me something to help clean? A robot says, I would. Let's see what it does. Find a Coke can. So it goes ahead and finds the Coke can and then says, pick it up. It picked it up. And then, go to the trash can. It went to the trash can, but it couldn't put the Coke inside the trash can. Then it goes ahead to find a sponge. So it is getting the things that it needs to do, like the common sense things of what do I need to do or the sequence of actions. But now let's see what it does after it picked up, this piece of sponge. It cannot clean the table, right? So again, what we are seeing is that the Moravec's paradox triumphs. The robot is unable to do these low-level skills which require physical intelligence. And the question really is, what is going to happen in 35 years from now? Would we have solved the problem, or would we be sitting and saying the Moravec's paradox still triumphs? Now, what is it that makes these low-level skills or the physical intelligence part be so hard? Let's go back and zoom out and look at evolution of life. So what I am drawing over here is starting of life and a timeline which goes until now. So it took almost 3.7 billion years when life started for apes to evolve. And what could apes do is some low-level skills of plucking fruits, going from branch to branch, notion of physical intelligence. Then it took around 15 to 20 million years for humans to come along. Then came language and reasoning, maybe in 4 to 5 billion years, right? And it's only been around 50,000 years since language emerged. Now, to put these things on a time scale that is easier for us to understand, let's imagine that we're doing the history of Earth in 24 hours. So it's midnight, and that is when the planet Earth is born. And in 24 hours is suppose our present. Then language is maybe only 10 seconds old. Humans came in maybe 1 minute, 20 seconds ago. Apes came in maybe 6 minutes ago, right? And life started 20 hours ago, right? There's some approximate numbers to get a sense of the time scale. And now, if we, go back to the dream of maybe building this robot which can do many of our household tasks, right? If I tell a robot, make me dinner, right? Then it's about language understanding, or understanding what humans like is, what is dinner? It requires us to know what humans eat, what are the recipes, what are the cooking steps. Then we have to actually execute it, which is the physical intelligence part, right? So now if you relate this on the time scale, right, understanding what is dinner maybe took 10 seconds to evolve, but this physical intelligence might take 20 hours to evolve. Now, if we see the success in AI today, ChatGPT being one of the prime examples, it is about language reasoning. So it's really solving this problem, which evolution took around 10 seconds. And it required all of the internet to get here. For the question which I am very interested in, the question which we need to solve to actually build physical intelligence, to have physical machines which can automate many of the tasks that we do as humans, the question is, how do we actually get here? Right? We just simply don't have this data available, right? Now, if you just go from 10 seconds, required all of the internet, 20 hours, wow, we don't know how to get there. And when we say by getting there, I don't mean specialized machines which can do one task. What I mean is, a general purpose system or an adaptive system or a generalist, which can do many of these things, right? So the question is, how do we actually build these adaptive agents? Now, to get a hint for this, let's go back and look at evolution. So what happened in evolution, when this physical intelligence was being evolved? So the one feature of evolution is that it would always put organisms with unseen environments, right? The temperatures of the earth would increase, they would decrease, there would be events like a meteor hitting the earth, and things would drastically change. So if an organism had to survive, instead of preparing for one task, what it had to do was to prepare for change, right? So if it overfit to one task, it will get extinct. But if it is adapting, it may survive for a long period of time, right? So maybe, what evolution did was to provide some bootstrapping to human learning in a manner that they can also adapt, right? So the question or the hypothesis being that evolution built in some mechanisms which help us adapt, right? And so we can, go look at babies, when they're born. What you notice is, they play around with things. Now, some of us might say that this play is essentially random, right? When, babies throw balls, put, objects in their mouth, push them, so on and so forth. But, there's one prominent line of thought in psychology which says that playing is actually a form of experimentation where infants are trying to learn about the world, how the world works, so that, they can plan for things and, perform functions when they grow old, but also, hone their skill of experimentation, which will help them adapt to new challenges thrown at them in the future. So what we can do is, we can take this principle of experimentation and try to build robots which also learn by experimentation instead of being specialized and programmed for one particular task. So this is, one, research theme that we have been exploring, how do robots learn by experimenting? So we took this, inspiration, and we had this robot, play around with this object, where it kept on pushing this object for a long time. Not just this object, but many other objects completely on its own. So what essentially is happening is the robot observes an object, it takes an action, which is an experiment it conducts, it observes the next state of this object. And essentially what we have is the state before, the action, and the state after. And it learns a model of some kind using this data. And then what we find is using these models, we can give our robots new tasks. For example, on the left-hand side, I'm showing the current state that the robot sees. On the right, the image is showing the goal state in which we desire the objects to go into. Now let's see what this robotic system ends up doing. It is able to manipulate new objects in a new configuration. Right? And it's not just about pushing. Right? We can let robots experiment with different kinds of things. On the bottom left, you're seeing a robot moving around in office environments. On bottom right, you see a robot playing around with ropes. Right? And after these robots have played around with objects, we can again give them tasks. For example, on the top right, I am giving this task to tie a knot. Right? And let's see, how the robot ends up performing this task. So what you see is, that the robot is able to go and tie a knot. Now just imagine if the robot was just playing around with the rope, and if its exploration was random, it wouldn't go and tie a knot. But somehow it was able to learn this, by playing around with the knob, how to tie the knot. Now, of course, the performance on this task is not 100%, it's around 60%, but it's giving us evidence that if the robot is learning from its own experiments, it can learn a model which can do some goal-directed actions. But now if you want a robot to perform more and more complex tasks, what we would want is for the robot to autonomously explore new things so it can continually keep on learning about new things and perform new tasks. So if the robot were to randomly explore, it is going to be very limiting. Let me illustrate this with help of an example. Suppose the agent is in the state shown by my arrow. If it takes an action, it goes to the next state. And if it takes a bunch of random actions, it's going to be constrained in what it explores. So instead of taking a random action, what we want is to take an action which is going to expand the knowledge of the robot, right? So how do we take these actions which expands the knowledge? Right? And the idea is that as the agent is exploring its environment, it is building a model of what happens next. And what it can do is it can take actions which violate its model, where the predictions are inaccurate. And what this will guide the robot is to visit new states, because in new states, the predictions are going to be off, right? And then this data can be utilized to improve the model, right? And then, when the robot has learned a new model, it will try to figure out where the model is broken, take those actions. Right? So now let me illustrate this with a more concrete example. Suppose we have this game screen of a Mario agent, right? It can go left, it can go right. If I press up, it goes up. If I press down, obviously it can't go, below the ground. So now, suppose we are building a model where we say, given the current state and an action, what happens next, right? The prediction is that if I go up, the agent is going to go up and go down. This is what happens in reality. But now suppose that the agent came close to a pillar, and this is the first time it has come close to a pillar. Now, if I press right, the agent would expect to go right because it has never seen a pillar or an obstacle before. But in reality, it will hit the pillar and not go right. So what we will have is prediction error. So now if we incentivize the agent to follow the prediction error or do actions which lead to errors, it will keep coming close to the pipe. And once in a while, when it is close to the pipe, if the agent says, if I press up, the expectation is the agent will go up and then come down. But in reality, this is what happens. The agent never goes down. It climbs up the pipe. So again, there is, this, distinction or a difference between prediction and reality. So if we make the agent curious by incentivizing prediction error, it can go and explore new things in the world. And what we found in one of the experiments was, if you let this curiosity algorithm run on the game of Mario, it discovers how to kill enemies, jump over pipes, all completely on its own, without getting any kind of reward from the game itself. Right? So what this experiment is suggesting is that we can develop algorithms which can be intelligent about how they explore the environment. Now, the agent is exploring the environment better, it leads to better models. Now, of course, there is going to be a lot to explore. For example, if you go to a library, you can read so many books, right? But if you want to do some particular tasks, somehow this exploration has to be biased. And this is where humans can come and they can provide hints about what to explore. Sometimes we can look at how humans are doing tasks, and this can provide hints or tell a robot how to do complex things. So it's really a combination of exploration, model building, and learning from humans, which can create this self-supervised learning loop where the agent keeps on exploring new and new things, which enables us to perform new tasks. Now, in theory, what I described you, seems like one potential mechanism for the robot to evolve and learn new things. But the problem is in scaling it up, because all the experiments which I showed you were about learning in the real world, which can become very slow. So what we have been looking at is how to scale this up. And one approach is really to train agents in simulation and then deploy them in the real world, which is called as going from simulation to real world or sim to real. But let me show you, one example first, starting with locomotion, where we are training these controllers or robots to walk in simulation. So this is the start of training where they hardly move. Give it some time and, the agents start to hop around and move. And if you let them, explore for a longer period of time, they learn how to walk, in simulation. And what we can do is we can take these models and overcome the differences of simulation from the real world and deploy them in the real world. Here is, one instance where this robot broke the speed record for this particular robot to run as fast as possible, right? But the cool thing is, it's not that it only walks on flat ground. It can also go on challenging terrains, like this ice, and spin on it, right, where it is very slippery, showing robustness. We can compare it with, baseline controllers, which are hand engineered for specific tasks, right? So they can do maybe fine on running on the ground, but now they fail when you have this unexpected scenario. Versus our system is able to, adapt to it and still keep on, walking. Here is another example where, you were experimenting with this robot. And at some point, what we found is that, one of the screws in the motors came out. So this robot is essentially limping at this point, but it still keeps on walking. showing the kind of robustness we can have in these systems. So now, once this robot is working, it can go and start doing other things. Right? For example, starting to play, soccer over here. Right? So what we can do is we can essentially build, this curriculum of tasks. But now instead of doing this in real world, doing this in simulation. Now we can look at another problem in the realm of manipulation. Right? Suppose we want robots to make food for us, and one thing we want them is to take a knife, grasp it, and then reorient it so I can cut the carrot. Right? This reorientation is required so that the sharp face of the knife actually faces the carrot. Right? As a human, we do this, all the time. Right? We picked up the screwdriver, reoriented it before we start screwing it in. And here are, some more examples of tool use, in humans, sometimes for fun, and sometimes it's actually necessary, right? So in the literature, we have made a lot of progress in grasping. And one of those ways has actually been to train in simulation and then transfer those policies for grasping in the real world. So I'm showing you this video from DexNet out of a lab at Berkeley, which was able to successfully transfer grasping policy. Now, this task of reorientation has, remained, hard in robotics, but we can again apply this philosophy of training in simulation, letting the robot experiment, where it learns in simulation to reorient objects. After some training, what we find is in simulation, the robot can reorient the object to the goal orientation shown on the left. And then we can take these policies, which were trained in simulation, and then deploy it in the real world. So we are showing this setup, which is less than $5,000. It has one camera, which looks at the object. And to be more precise, we get the observations from the camera, which is a point cloud, the joint positions of the fingers as input, and we output how to move the joints. This is just a side view of a setup, and we can evaluate it on novel objects. So here is one example where we want to orient this car into the shape shown on the top right. Right? Let's see what the system ends up doing. Right? It's able to orient this object in the correct pose. Right? It works for many objects. Here's another instance of an object the agent never saw before. It takes it, and it's able to reorient this object. And here is another example of reorienting a mug to the correct position. Okay. So what I am showing is evidence that we can also perform this learning by experimenting in simulation and keep on learning a sequence of tasks, first grasping and then reorientation. And hopefully the robot can learn more and more things, so it eventually comes to chopping vegetables. Right. So in some ways, this approach of doing things in simulation and transferring to the real world, I showed you in two different contexts, in context of locomotion and in context of manipulation. Turns out it's the same framework, similar code base, and we are seeing some very good, promising signs of this framework working. Of course, there are tons of open questions, but it's an exciting venue of investigation. So to summarize, in some ways, the current state of AI, things like ChatGPT and the kind of things we can do really well, like playing chess and so on, represent the last 10 seconds of evolution. I think the real question is, what happened in the development of physical intelligence? What happened from starting of life to the formation of apes to the formation of early humans? And one thing is that what evolution incentivizes is learning to adapt. And how do you adapt? Maybe one potential mechanism is by learning how to experiment. And this is some of the inspiration we have taken to, and we have started to build such robots. With that, I thank you for coming and listening to my talk. Thank you.